Hello again, everyone. The next speaker is Tosun. He is a student in Koç University in the Department of Electronics. Second year. Yes. Okay, his mentor is Gökcan Tatlı. He or he is not here now. So you can start.
Today I'm going to introduce you to Convex Optimization. Hello everyone. Today I'm going to introduce you to Convex Optimization. Convex Optimization is an important and recently studied field of optimization problems. And today we are going to introduce the basics of it. Flow of the content will be like this. We will first look up into the optimization mathematically. And we will look at the concept of convexity in sets, functions, and also optimization. And we will look at the historical background and significance of the field. And we will explore the foundations, and finally we will continue with convex relaxation, convexification process with some objects. And we will end the talk with a brief touch on CVXPy, the computational side of things. Optimization is a daily task. We all do it in everyday life, and it also has a mathematical definition, as you can see. Minimizing f0 of x with respect to such that fi of x is smaller or equal to bi is called an optimization problem. And in this case, we have an objective function which we are trying to minimize, which is the f0 of x. And we are trying to minimize it by changing the optimization variables, which are the x's in this case. And we have some constraint functions that can be one of these, and which are the fi's of x. And like I said, it's a daily thing when we do it all the times in every field of like dosage of a new drug could be an optimization variable, and the constraint function in that could be the lethal dose and the least effective dose, and the human physiology would also be a constraint for it. And the objective function in that case is the recovery time and the side effects. We are trying to minimize them, and this corresponds to the f0. And sampling rate of a sensor for a variable device could also be an optimization problem. And the noise and power consumption of the sensor and the noise of the signal will be objective functions. We are trying to reduce them. And the things that are making our life start are the battery capacity and range of sampling of the sensor. And we have all talked about the way of coming to Sabancı a few days ago, and it's also an optimization problem. Budget and transportation infrastructure were the constraint functions, and the objective function were time and the carbon footprints of transportation. Convexity is the other part of convex optimization, and convexity can be defined on lots of mathematical objects. And we have convex of sets. It is defined as a convex set is convex if the line segment throughout any 2 points in that set is entirely within the set. We call that set a convex set. And we mathematically define that as for every x1 and x2 in C, for a theta between 0 and 1, the convex combination of x1 and x2, which is defined as having theta and 1 minus theta of the variables, and they should add up to 1, and they should be positive, should be entirely within the C. And it can be geometrically interpreted as the same. We all know what convex geometrical shape is, and same as this. And convexity of functions can also be defined. A function going from Rn to R is convex if its domain is a convex function. set, and for all x and y in this domain, in that convex set, the image of the f convex combination of x and y should be smaller than equal to the convex combination of fx and fy's images. And we also know how it's looking in 2D or 3D case, and this is the. And the convex optimization is a kind of optimization where all the sets, all the functions, all the constraints, and everything is convex. And we are getting the advantage of this convexity in implementing a solution for these kind of functions. And if you think about it in a more general sense, we assume to think that if a problem is linear, it's easier to solve. But in fact, it can be extended to the convexity. If a problem is convex, we have the tools for understanding and solving them. And Tyler Rockefeller, an important optimization mathematician, had thought that, in fact, the great watershed in optimization isn't between linearity and nonlinearity, but convexity and non-convexity. We have the mathematical methods and also the understanding of finding the most optimal solutions and proving that it is the most optimal solution for convex problems. If we have convex constraints and convex function and convex set, we can prove that it is the most efficient way of doing things. And we have some classes of problems. First one is the least square problems. I know every one of you know it. And we have the analytical solution for that. And there are also linear programming problems, like I said, the linear ones. But there are also non-linear convex optimization problems. We also have ways of solving them for them. And least square problems and linear programming problems are also a part of convex optimization problems. And we have methods to solve them. It's not that common to see a mathematical method making its way into the newspapers. In 1984, in the New York Times magazine, it had made its way into the headlines, and it was on the cover page, breakthrough in problem solving. The Bell Labs mathematician and Karmakar found a new and effective way of solving linear programming problems called the interior point method. And it was implemented in the industry before even the publication of the original paper. It was already started to use in lots of industrial applications in aeronautics area. And it really shows the importance of convex optimization in a more commercial sense. A brief history of optimization. It has been studied since 1900s, so it's an old field, older than most of the neural networks and popular problems in mathematics. And the algorithms for it were started to implemented by the development of the computers. 1947, the simplex algorithm for linear programming were introduced. And in 1970s, in Soviet Union, ellipsoid methods were introduced for solving these kind of convex optimization problems. And throughout the 80s and 90s, polynomial time interior point methods were developed, and they were really optimal for low-cost problem solving. And with the development of big-scale computers, large-scale methods and algorithms were introduced. And we can see that the development of the algorithms were in parallel with the development of the computer technology. It's not that really efficient to solve the convex optimization problems with pen and paper, but it's really efficient to solve them with computers, and we will see that. Yeah. And where it is used, in 50s, it was used in aerospace industry. In 60s, it was started to use in filter designs, and we are still using them. One of the most popular filters, the Kalman filter, like used in reinforcement learning, is based on convex optimization as well, especially least square problems optimization. And before 19th, it was used in operational research for the development of supply chains and this kind of. And throughout the 19th, it was started to implement it in lots of areas of electrical engineering, signal processing, communication, service. And since the 2000s, it's used in machine learning, statistics, and neural networks. So it has lots of different usages. For the foundations, the convex analysis can be thought as the linear algebra with asymmetries. What do I mean by that? In linear algebra, we do not have that much of constraints. Like we do not say it should be positive, it should be negative. But in convex optimization, we generally have these kind of constraints. Like we are concerned with some side of things, like we have asymmetry, we are concerned with the positive side of things. And because of that, we are dealing with the same concepts as linear algebra, and they can start from a vector and eigenvalues and matrices and norms and lots of different parts of linear algebra that carry information. And why are we trying to understand linearity and extend it to convexity? Because we are trying to extrapolate local behaviors of functions into global properties. What do I mean by that? We all do that. We use gradients, which is a infinitesimal local behavior of a function, and we are using that to find the global property of a function. And by doing that, we are reducing our consumption costs, and we do that for lots of different convex problems. Convexity is more simple to analyze, and we have the methods. We try to make our problems modeled with convex formulations, with convex functions and other things. And we are trying to achieve that convexity by convex relaxation in a vector sense. We have L0 norm. L0 norm is defined as a number of non-zero entries of a vector. And in computation, we are generally trying to minimize that, to minimize the computation costs and also the power consumption. And we are getting to trying to get a more sparse vector, and we are trying to maximize the number of zeros. But this is not a convex function, and trying to minimize that with our methods is not really working. So we introduced the L1 norm, which is a convex function over vectors, and can be minimized with convex optimization methods. And it is defined as being the sum of absolute values of entries of vector. If you think about it, if you are lowering that, you are generally, in the most cases, also lowering the L0 norm of the vector. And we also have the same case for the matrices. We have the rank, as you all know, which is number of non-zero eigenvalues or number of linearly independent columns, which gives information about the matrix. And we are also trying to minimize that because of the same reasons as minimizing the norm. But this also is not a convex function of matrices. But there are lots of rank minimization problems, especially in signal processing. And we introduced the nuclear norm, which is the convex relaxation of rank. And it is defined as the sum of its singular values, which are the positive eigenvalues of A transpose of A. And like I said, it has some asymmetries, like we are taking the square root of on the positive eigenvalues. And the nuclear norm is a convex function, and we can take advantage of the minimization methods, like I said. And the convex hull is the most general set of relaxation. And convex hull is the smallest convex set that contains a specific set that may not be convex. Like here in that example, we have a region set, but as you can see, it's concave, it's not convex. We can extend it to a convex form, but it's not minimum, and we are generally trying to minimize it to reduce the computation cost. And the convex hull is the smallest set that contains the original region, but it's convex. And the things I have said are also convex hulls. Like M1 unit norm ball is the convex hull of L0 unit norm ball. You can see L0 unit norm ball in two-dimensional plane. And the convex hull of it would be that region, and we are connecting the endpoints of that, and we get the L1 norm. The same thing can be taught about the nuclear norm of the convex hull of rank-1 matrix with a spectral norm, Barnett Y1. Since it has a more complex representation in higher dimensions, we cannot see, but it's the same thing for all the things, and we are trying to get to the convex sampling. And we finally have CVXPy, which is the Python-based, the convex Python, the name suggests, Python-based modeling language that is suitable for solving convex optimization problems. And it is an object-oriented programming language. And it has some objects, and the first object corresponds to the optimization variables, which is called the variable. Second object is problem, which is corresponding to the constraint functions of optimization problem. And we also have the minimize object, which is the objective functions correspondence. And there are lots of great examples and also some problems and Discord server. If you are into that, you can look it up and try to solve convex optimization problems really efficient. I think you will benefit from it, especially if you are working in industry. Finally, we have seen that convex optimization is used in lots of different fields, ranging from signal processing to operational research to aeronautics to biology, even maybe statistics. Almost every field can benefit from it. It's a well-established field. Its foundations were laid pretty solidly, and it is still being built on up. And it's integrated with technology. It was developed, it was evolution alongside technology, computation technology. And we also have CBXI, which is really and it has fast and reliable algorithms and methods, and it's really important. And if you have a foundation in linear algebra, and I'm sure every one of us have some, you could look it up if you're interested. And that's all for me. Thank you for listening.